its name, Mergesort. Yeah, so this is another interesting sorting algorithm. C.1, Introduction to Mergesort. First, let me explain the motivation for this sorting algorithm, because this is our, so let's look at what sorting algorithms we have learned at this point. Selection sort, bubble sort, insertion sort. Now, number 4, merge sort. Yeah. All right. So why? What's the reason we want to develop another sorting algorithm? Yeah. So here, let me explain. Yeah. Problem number 13, merge two sorted arrays. Yeah. Here we consider a special operation, merge two sorted arrays. Why we consider this special operation? Yeah, I give you the reason. Yeah. Here, let me describe a special problem we need to solve. Yeah. You can imagine, some real-world situation, we may have chance to solve this kind of problem. Yeah. Given two ordered arrays, we already know each one is ordered, two ordered arrays. Yeah. Now we want to do this operation. How to merge them to get an ordered array, bigger ordered array. That ordered array contains all the elements from these two ordered arrays, and we want to use the minimum number of comparisons to solve the problem. That's our problem number 13. Yeah. It's hard. It's not hard. Yeah. First, it's not hard. Yeah. Pretty simple. Yeah. But before I go through the solution, let me give you the background, the motivation. Yeah. Give you a special situation that we need to solve this problem. Okay. All right. Why we need to consider this problem? Let's consider a special case. We want to sort a huge array. Yeah. Before we look at this question, currently, when we do the sorting, we at this point, we didn't consider the limitation of our computer, right? Yeah, I never talk about that. Currently, when we do the sorting, we didn't consider the limitation of our computer. So what do you mean the limitation of computer here? Yeah, think about, so let me explain this limitation issue. Yeah, because in the real world situation, you need to prepare for any possible cases, right? Yeah, whatever it happens, you need to find a solution. Yeah, so here we need to consider some computer limitations. What kind of computer limitations? Yeah, let me describe it here. We know computer, so here I use the space here. In the computer, all right, we have memory, main memory, and hard drive, right? Hard drive, okay, yeah. The data originally stored in hard drive. So our array, yeah, that's our data originally stored in hard drive. But in order to do processing, the data needs to be loaded in main memory for processing, right? So loaded into the main memory to do processing. Because if the data stays in the hard drive, not loaded into memory, you cannot do any processing, okay? You cannot do any manipulation. Yeah, so you have to load it into the main memory. But now the question, we know the main memory much smaller than hard drive. Yeah, main memory, we know usually several gigabytes. Okay, yeah. Hard drive could be as large as the terabytes, right? Let's imagine, okay? Or at least hundreds of times, okay? Yeah. For simplicity, let's just assume 1 TB, okay? 1 TB, that's the size of our hard drive, but our main memory is several gigabytes, okay? Yeah. So then there is a possibility if our data size is too large, we cannot load it into the main memory. We cannot load all our data into the main memory at once. Think about that. When that happens, how do you do the sorting? So that's the background behind this huge array. How huge it is. The size of the data is much larger than the size of the main memory. That huge. Think about that. Oh, we know it's rare, right? You can argue it is rare, yeah. But when that extreme situation happens, you need to solve the problem, right? Yeah. So here, we need to solve the problem. So how to do it? Let's assume this is the size of a huge array that cannot be loaded into the main memory at once. Then we use divide and conquer. The topic of this module, divide and conquer. We can divide it into several smaller pieces, and each piece can be loaded into the main memory. How about that? Okay, yeah. So we divide it into several subarrays and make sure each subarray can be loaded into the main memory at once. Yeah. So that idea, okay? Then we can apply some sorting algorithm to sort each subarray. How about that? Yeah. After we load each subarray, then we just run our usual sorting algorithm. We can get it sorted, okay? So you can imagine each subarray is sorted in order, okay? Each sorted in order. After that, our goal is to make the whole array sorted. Do you think the next step we need to do, can you relate it to the merge step I just described it above, right? Because if we consider two subarrays, each one already sorted. So the next thing we need to do, merge these two ordered arrays. That's the problem number 13 we need to solve. Okay. If we have that solution, we can apply that merge operation on every two subarrays, two ordered subarrays. So we can merge to get one bigger subarray, okay? And so on. Yeah. Eventually, yeah, we get the whole array sorted. Yeah. So that's the reason, motivation. Yeah. So we may need to apply this merge operation. Yeah. All right. So next, because if you can split, divide, and conquer, you can take advantage of parallel computing. Another reason we may need to split a big array, because right now the parallel computing, multiprocessors, very common, right? Think about multiprocessors, very common. Multi-core, okay, think about 128 core processor. Yeah, think about that. Yeah. So in order to take advantage of the parallel computing, so we can split into subarrays and make those parallel processors to do the sorting. Yeah. So after that, then we do the merge operations. Yeah. So we can, in that way, we can do sorting faster. Okay. So another reason we may need this merge operation. Okay. Yeah. Next, let us find a solution. Yeah. This merge operation, although it's not hard, yeah, but we need to find its solution. Yeah. All right. How to merge two sorted arrays? Yeah. Given two arrays that are already sorted, how to get a new sorted array that contains all the elements. Yeah. Okay. All right. Here, when we do the merge, we should not run any sorting algorithm for the data we have another time, because that won't, in that way, we do not take advantage of the structured data. We already, because the structure of the current data is very good, we should use that structure. We should take advantage of that structure so that we can use much fewer number of comparisons. If you do not take advantage of that structure, nice structure, you just apply a sorting algorithm on the data combined from both subarrays, then your performance could be very slow. Okay, yeah. Here, the main thing, we should not start over again, just run the sorting algorithm in some blind way, yeah, because you do not consider any special structure you already have. Just run some sorting algorithm in a blind way. Then you won't get good performance. Yeah. Here, we want to do it in a smart way. The smart way, the nice structure, each one already ordered, that structure can help us reduce large number of comparisons. So that's what we are going to do here. Yeah. All right. Do not use any sort that does not, yeah. So that's what I said. Yeah. So you need to really explore the special structure in these two subarrays. Yeah. All right. But here, let us consider, based on our experience, we have learned three sorting algorithms: selection sort, bubble sort, and insertion sort. Yeah. And we want to borrow some experience from these three sorting algorithms. Yeah. But we need to pick the right one. So which one can provide us some helpful experience. Yeah. So that's something we need. Yeah. But when we do our selection, we want to see which one of the three gives us the property that can take advantage of the ordered information. That's something we need. So which one can take advantage of ordered information of the data? That's the one we need to borrow some experience, borrow its, solution, idea of the solution. Yeah. First, let's look at a selection sort. Let's recall for the selection sort, when the array is already ordered, when the array is already ordered, if we apply selection sort, can we get a better efficiency? If the array, we know it's already ordered, but we just assume we do not know it. We apply selection sort on this ordered array. Do you think we will get a better efficiency? The answer is no. Even if it is ordered for the selection sort, you get a big, let me right here, big theta of n squared. Okay, even if it is ordered, because I assume you know the details of the selection sort, because every time we find the minimum, okay, the first time finding the minimum, we get n minus 1 comparison, second time n minus 2 comparison, and so on. Okay, even it is already sorted, you still, because you cannot see it, right? You cannot. In computer, when you run computer algorithms, computer does not have eyes, so computer cannot see it is sorted. Okay, it still use the selection sort step by step from beginning to end, so the performance still, it will be big theta of n squared. So for the selection sort, it does not help. Okay, it does not take advantage of the order information. So we should not consider selection sort. All right, bubble sort. Bubble sort, if the array is already ordered, still big theta of n squared. Doesn't help. The same reason as that of the selection sort. It doesn't help. But insertion sort, we learned last time, insertion sort, then it's different. Insertion sort, if the array is already ordered, then the efficiency is big theta of n. It is greatly reduced. It is reduced from n squared to big theta of n. That's a big improvement. That means the solution of the insertion sort, it helps us a lot. So we should borrow the solution from insertion sort, or the idea of the solution from the insertion sort to solve our current merge to ordered array problem. So, all right. So when we work on the solution, we consider that insertion step. Because the main step of the insertion sort is the insertion step. So the insertion step should shed some light to our new solution. Shed some light. Okay, all right. We know insertion sort has some good property. This is the good property. Good for almost ordered array. Yeah. But here we have two ordered array. If we put them together, we can treat as a special case for the almost ordered array. Yeah. Although not exact what we mean last time, yeah, but sort of. Yeah, let's say this, sort of. Yeah. Not exactly what we describe it. So what we described last time, almost sorted. But sort of. Yeah. All right.